Section 2.8, we start looking at two variable inequalities. We've been graphing transformations of different types of functions, right? Lines, absolute value graphs, things like that. We're going to start looking at two variable inequalities today, both linear and absolute value ones. A linear inequality is a two variable inequality whose graph is a region of the coordinate plane bounded by a line. So instead of just a line, we now have some of our coordinate plane shaded as well. Okay. The boundary line can be dotted or solid, depending on the type of inequality you have. And the shaded part is called a half plane. All right, we're basically saying half of the coordinate plane are solutions to that. That means any point in this shaded area would work in that inequality. It would be a solution. A point on a dotted line is not a solution. A point on the solid line is. Okay, kind of like your open and closed dots when you graph on a number line. Okay, same thing here. A solid line means we can include the values on that line. Okay, so are points on the boundary line considered solutions? Only when a solid line. Okay, dotted lines means we get really close to that, but we aren't actually on the line. So our process for graphing, we typically have two types of equations. We have the ones that are in slope-intercept form that look like that y equals mx plus b format. And we have the type in standard form, ax plus by equals c. I don't want you to have to convert them all into slope-intercept form. So we're going to look at how do we graph when they're in each of those forms. In slope-intercept, you identify the slope and the y-intercept from the graph. You plot your y-intercept, and you count rise and run, right? You sketch the slope out. We use a dashed line if there's no equality part. We use a solid line if there is an equality part. Okay? For a slope-intercept version, we are able to shade the half plane based on the inequality we see. So if you have y is greater than or y is greater than or equal to, you're going to be shading above the line. If it says y has to be less than or less than the equal to, then you're going to be below the line. Okay? If we are in standard form, we cannot identify slope and y-intercept just by looking at the equation. So instead, we're going to make our t-chart and find our x and y-intercepts. Okay, we graphed this way earlier in this chapter. Same thing applies for solid and dotted lines. The difference here is, again, we can't tell just by looking at the equation which half plane to shade. So we actually have to test a point. The easiest point to use is the origin. The only time you can't use that as your test point is if your line actually goes through the origin. You're trying to pick a point that's not on your line. Okay, let's try a couple of these. What form is the first one in? Slope-intercept. Yep. So what is the y-intercept? -1. So we know we're going to start our graph here at -1. What's the slope? Okay, so we're going to do a slope of 3. So we're going to rise 3, run 1. Have enough points that you can get an accurate line. Will the line be solid or dotted? Solid, because of that equal sign. So go ahead and draw a solid line through there. Check that you've put arrows at the ends. Now, we want all y values that are less than or equal to the points on that line. Okay? That means we need to be underneath the line or on the line. So we would have our solid line and we would shade all the values underneath. Okay? Example 2, same format. Where do we start? Start at the y-intercept of 1, and our slope is -2. So down 2, right 1. Solid or dotted line? Dotted this time. Try to get your line to actually go through your dots. Are we going to shade above or below that? Above? Are we agreeing on that? Above? All right. How is this next one different? There's no y. This is technically in standard form. If there's no y, you can't put it in y equals mx plus b format, right? So this would be considered standard form. But we're missing the y value. So how would we show x equaling 4? What would that look like? What kind of line do we have? Vertical line. X equals 4 is going to be a vertical line through 4. Yes? Now, that would just be x equals 4. We want x to be greater than 4. What would have to change? It should be a dotted line, okay? Since it can't equal 4, we're just getting close to it. And then which side, which half plane would we shade? We want x values bigger than 4. That would be things like 5, 6, 7. Yes? So we're shading over here. Okay. The other one here, example 4, is in standard form. We are going to find our x and y intercepts. So what happens when we put a 0 in for y? So we end up with -3x has to be less than or equal to 8. When you're finding intercepts, don't worry about the inequality part. Just pretend there's an equal sign there. All right, you're trying to find the boundary line, and then we'll analyze if it should be solid or dotted after that. Okay? So we've got -3x has to equal 8. X would then be -8/3. Okay, where is that? -8/3. As a mixed number, it would be what? -2 and 2/3? Okay, so -2 and 2/3, put a dot. Now we're going to go back and instead, we're going to put a 0 in for the x, which makes that first piece 0. 2y has to equal 8. Y would be 4. That's my y-intercept. Okay? Solid or dotted line? Solid line, connecting those two dots. And then we need to test a point. If we have both an x and a y in our equation and it's in standard form, we have to test a point. I'm going to test the origin because it's easy to plug in zeros. But you can test any point as long as it's not on your line. Okay? So if we go back up here and we put in 0 for x and y, that whole left side becomes 0. Look at the remaining statement. Is 0 less than or equal to 8? 0 is less than 8? Okay, so we shade the side that has our test point on because our test point worked. If your test point doesn't work, in other words, it gives you an inequality that's not true, you don't have to test another point. If we test a point and it works, it means every spot in the same half plane where that test point is a solution. If it doesn't work, it means we need to shade all the other half plane. Does that make sense? So it's an all or nothing thing. If the point works, shade the side it's on. If it doesn't work, shade the other side. All right. Our next two, we've reversed it on you. I've given you the graph, and I want you to come up with the inequality. Okay? We're going to write these in slope-intercept form. That's our easiest way. Can we identify the intercept and slope from this graph? Okay? Intercept is -1. That'll be the b part of my mx plus b. What's my slope? Looks like we're rising 3, running 1. So slope is 3. So if I were just writing an equation for the line, I'd say y equals 3x minus 1. All right, but it's a dotted line. So instead of an equal sign, I'm not going to have that. I'm going to have less than or greater than. And I look at the side that's been shaded. Since it's underneath, what does that tell me? Has to be less than. Okay? I'm going to pause the recording for a second. I want you guys to try the next one. All right, for the second one here, our intercept is at -6. Our slope is what? And because it's going down, it is -1, right? We're going down 1 over 1. So our slope is -1. It's a solid line, which means we can have an equal sign. And we're shading below, which means less than. Okay? Questions about that one? All right. Take a minute and read through the next example. Talk with your partners about your starting process. I don't want you to actually solve it, just how would you get it started? So in example 6, it says we're going to go to the fair to go on the rides. We don't want to spend more than $15. Tickets are 25 cents. The small rides require 3 tickets. The large rides require 5 tickets. How many small or large rides can we go on? We could do all small rides. We could do all large rides. Or we could do a combination of them. Yes? There's 2 things they're asking us for. How many small rides? I'm going to use an X for that. How many large rides? I'm going to use a Y for that. So on my graph, I'm going to set this up okay, number of small rides for the x-axis and number of large rides for the y-axis. How many tickets does it take to go on a small ride? 3. So if I want to go on 10 small rides, I would need 30 tickets. If I want to go on 5 small rides, I would need 15. So however many small rides I want to go on, I need 3 tickets. Yes? How about for the large rides? I need 5 for each one of those? Okay. There is a limit in terms of money, but this equation deals with number of tickets. Why did they tell us the money part? Can we use the money information to figure out how many tickets we can buy? Yes? Okay. So right here, if it's 25 cents for a ticket and we don't want to go over our $15, 25 cents for each ticket has to be less than or equal to 15, right? We don't want to go over that. So how many tickets is that? 60 divided by 1, or sorry, 15 divided by 1/4 is the same as 15 times 4, which is 60. So we can buy 60 tickets. How we want to split those up in terms of the small and large rides is up to us. Yes? So the 3x plus the 5y has to be less than or equal to 60 because I can't buy more than that. Does that make sense? All right. That is in standard form, so let's go ahead and find our intercepts. If I go on no large rides, all small rides, how many can I go on? 20. If I don't go on any small rides, what's 60 divided by 5? I could go on 12 large rides. All right. So plotting those points, 20 is the far point over here for x. And 12 for y. Before we draw the line in, why did I only give you quadrant 1 for a graph? We can't go on negative small rides, negative large rides, correct? So we are limited to just quadrant 1. So instead of a line through the whole coordinate plane, we really just have first quadrant. Yes? All right. Most students will shade here. Why am I shading underneath? Do I have enough tickets to go on no rides? Yeah. I'm not going to have any fun, but I have enough tickets for it. Do I have enough tickets to go on 3 small and no large? Do I have enough tickets to go on 3 small and 2 large? Do I have enough tickets to go on 3 small and however many that is, large? Yes? So all the points underneath my line work. Can I go on 2.5 small rides? So in this case, the accurate drawing would be a dot on each of these corners, filling this whole thing in with just dots on the corners. But that's a lot of dots, right? So we do shade it to say everything below here works. But the understanding is that this is what we call a discrete situation, where it's not every point that we're shading, it's just the whole number ones. Does that make sense? So I'm fine with you shading the whole part of the graph underneath your line, but understand that really we can't do the halves and thirds and things like that. Okay? All right. The last part that we're going to look at is the same thing, but instead of lines, with absolute value graphs. What shape are the absolute value graphs? What shape are the absolute value graphs? When we go to graph those V-shaped absolute value graphs, it's easiest if it's solved for y. All right? A lot of times it's already given to us in that form, but if it's not, we want to get y by itself. We're then going to graph it using our transformation idea. Have we moved it left, right, up, down? Have we stretched or compressed or reflected it? The only difference today is that we might have a dotted V instead of a solid one, and we're going to shade. Okay? So describe for me the transformations for this first one. Are we in agreement? Right 2, down 5? Okay. No change in the slope? We haven't stretched or compressed or flipped. Okay? So the slope on the right side would be just a 1. All right. Let's plot our vertex. We're going to go right 2 and down 5. On the right side, we're going to graph a slope of 1. On the left side, we do the reverse, slope of -1. Will this V be solid or dotted? Okay. Double check that you are putting arrows on the ends. And just like with the lines, analyze your inequality. If y has to be less than or equal to that, it's going to be on which side? Inside the V or underneath the V? Okay, so we want to be outside the V down here, right? We want to be below the line, or in this case, below the V. Okay. What are we doing to this one? Okay, there's a vertical stretch. What else? Left 3 and up 1. All right, let's find our vertex. Left 3, up 1. This time we're going to graph with a slope of 2 on the right side. So up 2, right 1. On the left side, we're going to go up 2, back 1. Will it be solid or dotted? This one should be dotted. If we want y to be greater than that, that means we have to be above our line or above our V. In this case, above would be everything inside. Questions on that? All right. What's different about these next two? There's numbers on the side with y. Okay? This is why I said we need to make sure and solve for y first. All right. How do we get that 4 out of there? All right, so we're going to make it look like this. Yes? And now it's the same thing we've been graphing. All right. Shifting which way? Right 1 and up 4. And we have a slope of 2. All right. So a slope of 2. Solid or dotted? Solid. Are we shading inside the V or outside, below the V? Inside? All right. Our last graph, we have to be careful. Why? So if I'm trying to get y by itself, my first step would be to move the 1 over, subtract it over, but that leaves me a negative y. How do we get rid of that negative? Divide it over. Has the same effect as multiplying it over, right? If we multiply both sides by -1. We have y here. How we're going to show this on the right-hand side? We are multiplying the absolute value piece by a negative. Yes? The -1 on the outside here is going to become a +1. And what's the one other thing we have to remember to do? Flip the sign. Instead of less than, we're going to have greater than. What happens when I have that negative in front? It's reflecting. So now my V is going to be upside down, right? So we're going to reflect over the x-axis. We're going to go left 2 and up 1. So left 2, up 1. Reflecting means now on the right-hand side I have a -1 slope. And on the left side I have a +1 slope. Solid or dotted? Dotted. Shading above or below? Look at our new one. Shading above or below? Above. That's why I'm asking these questions, because with absolute values, inside, outside, above, below, it depends on which way your V is pointing, right? If we want to be greater than, we have to be above the V. So in this case, above the V is outside of it. Yes? Now, if we weren't sure, could we test a point? Sure. Let's try putting in 0, 0. It's not on my V. I can test it. Put a 0 here. We'll put it in our original one. The left side becomes 1. The right side becomes the absolute value of 2, which is 2. Is 1 less than 2? So it works. So we want to shade where the origin is. Okay? All right, our last two are the reverse again. I give you the picture, you tell me the equation. So for this first one, it's dotted, which means there's no equal sign. We are shading above the V. So what kind of symbol? Greater than? All right, where have we moved it to? Our vertex. Where did it move to? It went right 3 and down 2. So right 3, down 2. And our slope on the right side, what's our slope? 1? You can write the 1 in if you want. You don't need it. Okay? For this one, we are above the V. So greater than again. It's dotted. Vertex moved to where? Be careful here. Our tick marks are going by 2's on this one. So we went to -4, so left 4. And then we went up 3. What's the slope on the right side? We're going down 1/2 over 1/2, or down 1.5 over 1.5. Yes? So the slope is -1? Yes? No? I'm talking about squares. Down 1.5 squares over 1.5 squares? Yes? Okay. Down 3 over 3? Same thing. -1 for a slope. You can count squares as long as the tick marks are going by the same increments on both x and y. Right? All right. So assignment is listed here. I will get you some graph paper.